course, as you know from working with simulations, the more galaxies you add in, the initial conditions get harder to match, et cetera, et cetera. But yeah, SAG is another one, but we do have a collaborator thinking about what that impact will be. But our guess is that given the mass ratio between SAG and the LMC, it'll be less important, and therefore it might be okay to at least not include it in all of our models, but it's sort of still work in progress. So it's a great question. Thanks.
I'll take that. Up next, we have Cunningham, who's going to keep us close to home and talk to us about other substantial Butsky neighbor who is, making quite a bit of a mess all over the side.
Thank you. Good. I got it hooked on. How's volume? Good. Great. I feel like that was just the perfect introductions. Thank you so much, Ekta. Thank you, Rohan. I want to kick off this talk with an apology. I'm so sorry that I'm actually late to this meeting. I got married on Saturday, so it's been a real week. I missed your talk earlier in this week. I really sincerely apologize. Please come introduce yourself to me if I don't know you already. My name is Emily Cunningham, and I'm a Hubble Fellow at Columbia. And today I'm going to tell you about my research program more broadly on stellar halos, but then also get into a specific recent result that we've had related to the Sagittarius stream, which we just got introduced to. So this is perfect. So let's talk about stellar halos. So Milky Way is a spiral galaxy that is embedded in a huge halo of dark matter, and strewn throughout that dark matter are stars. And this is the component known as the stellar halo. So here I'm showing you an image from the Latte suite of Fire 2 simulations, where we have a beautiful spiral galaxy embedded. I don't know if it's kind of hard to see on the screen, but it's embedded in a very diffuse but also structured stellar component. And this is the stellar halo. So it's really useful that the Milky Way has a stellar halo, because we can use the motions of these very distant stars to trace the underlying mass distribution of the Milky Way and study the Milky Way's dark matter halo. So how did the Milky Way get its dark matter halo? We think primarily through the accretion of dwarf galaxies. So here I'm showing you a very classic simulation suite, Bullock and Johnston from 2005, where we believe the Milky Way assembled its dark matter halo over cosmic time by consuming smaller dark matter halos, some of which contain dwarf galaxies. And so it's the remains of these dwarf galaxies that make up the component of the stellar halo. So while we can use them to trace the mass distribution of the Milky Way, we can also use them to study the dwarf galaxies that contributed to the Milky Way's buildup over time. And so we have this special window to study these disrupted systems that didn't survive until present day and are too faint to observe at high redshift, but from within the Milky Way stellar halo. And the way we do that is by measuring the motions of stars and the positions of stars, and also studying their chemical properties, since their chemical properties are imprinted with the environment in which they formed in these disrupted dwarf galaxies. So I want to take a moment to just acknowledge how much this field has changed even in the course of my career. So this is a screenshot of my very first paper that I wrote as a graduate student in 2016, where I published the 3D motions, so proper motion and radial velocity, for 13 Milky Way halo stars. And these 13 stars were the first sample of 13 stars outside of the immediate vicinity of our sun to have these measured 3D motions. Fast forward to today, now we have the Gaia mission, which has measured the proper motions for over 1 billion stars in our galaxy. So we've had this huge explosion of data coming in to really study the Milky Way in more detail than we ever thought possible. It has completely transformed the field. So Gaia, in conjunction with a lot of amazing spectroscopic follow-up programs, has really just changed our whole paradigm for how the Milky Way evolved. The Milky Way's in disequilibrium. We've learned so much. So it's been such an exciting time to be a part of this field. And I, for one, am relieved to not just be talking about 13 stars anymore, because that got old. So in conjunction with these tremendous advances on the data side, we've also, of course, had tremendous advances on the theoretical side, where we saw some beautiful movies of cosmological students in Cassie's talk just earlier this morning. This is a movie from the Fire simulations, where we have these beautiful high-resolution hydrodynamical simulations of galaxies and, for my particular interest, stellar halos forming in these realistic environments. And so what I like to do is use the cosmological simulations as tools to say, what are the right questions we need to be asking of these amazing data sets that we have available? And then to go to the data and say, okay, this is what I think I'm seeing in the data. Does this make any sense in the sense of the cosmological simulations? And go back and forth between the two. So that's how I think about my work. So I motivated this talk by saying, we can use halo stars to trace the Milky Way's mass distribution and dark matter halo, as well as study the dwarf galaxies that didn't survive until present day. And the perfect intersection of these two questions is the Sagittarius stream. So as we were just hearing about, the Sagittarius stream is the most massive stream in the Milky Way. It is a very special system in that it has an intact core, the Sag dwarf spheroidal, and then these very extensive tidal arms that extend out to over 100 kiloparsecs in the galaxy. It's in every halo sample and every halo survey because its debris really is everywhere. And since its discovery, it's been really powerful in constraining our knowledge of the Milky Way's dark matter potential because it extends so far out into the halo. Matching the debris has been a very powerful tool for estimating the mass, the halo shape of the Milky Way. However, there's still a lot of uncertainty about the initial conditions of this interaction. In particular, the mass of Sagittarius remains uncertain to really within a factor of 10. And so it's really important that we understand Sagittarius as a dwarf galaxy before it's disrupted, if we want to use it to then constrain the properties of the Milky Way dark matter halo and interpret our simulations. Now, one tool at our disposal for constraining the mass is stellar chemistry, because mean stellar mass correlates with mean stellar metallicity in dwarf galaxies. But this is complicated by the fact that there's been a number of studies that have argued that Sagittarius would have had a metallicity gradient prior to being disrupted, such that its mean metallicity changes as a function of radius. And this is observed in many dwarf galaxies. So I want to highlight just two particular studies here from Chris Hayes, who looked at this with apogee, where these are stars that are in the core of Sagittarius, and these are stream stars. And you can see the stream stars are not as metal rich as the stars in the core. There was also a really nice paper from Guilherme Limburg just this past year showing that if you look at lower and lower metallicities and compare to a simulation, the metal core stars are consistent with both the current wrap of Sagittarius as well as the previous wrap, because we think it wraps around the galaxy several times. But one thing I want to highlight in these two figures is that you can kind of tell that the number of stars that we're working with is not that much. It's on the order of a few hundred, maybe up to 1,000 stars. And so because these observations are very expensive, it's been difficult to really get a handle on what was this metallicity gradient and what's going on in Sag prior to disruption. So what we've done this past year is study the Sagittarius stream with Gaia. So here I'm showing you a metallicity map of the Sagittarius stream. So I plotted this in Sagittarius stream coordinates. So the remnant, the Sagittarius dwarf galaxy remnant, is approximately 0, 0 in this figure. This is the leading arm. So these are the stars that are ahead of Sagittarius remnant in its orbit. And this is the trailing arm behind it. This is stream longitude on the x-axis and stream latitude on the y-axis. So if I say along the stream, I mean with stream longitude. And if I say across the stream, I mean with stream latitude. So this is a sample of 34,000 stars that are likely Sag members that have their metallicities inferred from Gaia BP-ARP spectra. Now, these BP-ARP spectra are one of the really exciting data products from Gaia DR3. They are very low resolution spectra that a number of groups have shown with the right model and with the right inputs, you can actually get a lot of information from these low resolution spectra. So this particular catalog that I used was from René André. And so this sample of 34,000 stars in Sagittarius with chemical information is over an order of magnitude more stars than we've had to work with before in Sagittarius. And it's because we have Gaia, we have all sky, and we have these incredible low resolution spectra that have been shown to be very informative. So what we did was look at the metallicity trends with stream coordinates. So in the bottom panel, I'm showing you the trends with stream longitude, which other studies have looked at before. There's a little nuance there. What we find is broadly consistent with what other groups have found when you look as a function of stream longitude. But what I want to highlight is that we actually see a gradient with stream latitude, so perpendicular to the stream for the first time. And this hadn't been seen in any other studies, in part because they were very limited by small numbers of stars, as well as incomplete stream coverage, because again, these observations are very expensive. Cool, so what does this mean? What do we do with this? Should we have expected to see this? Let's turn to a simulation to see what we should have expected. So here I'm showing you a map of a simulated Sagittarius stream. I want to advertise that these simulations were run by Columbia undergraduate. You want a Stelea working with Jason Hunt. You want to starting grad school just the semester at UW-Madison. So please watch out for their paper. This is a map of the Sagittarius stream in simulations, but instead of color coding by metallicity, here I'm color coding by initial radius within Sagittarius. So this block here is the core. A lot of these stars were closer into Sagittarius before it was disrupted, whereas these darker regions are stars that are more in the outskirts. And when we decompose this into trends with stream coordinates, we see trends that look essentially identical to what we're seeing in our data. So we see that this gradient perpendicular to stream is actually very naturally expected if our more metal-poor stars were in the outskirts of Sagittarius compared to the more metal-rich stars in the core. And so to get a little more quantitative, what we can do is we can paint metallicities onto our simulation and compare with the data to see what different metallicity gradients give us a result that's consistent with what we're seeing in the data. So here the data are shown in gray, and I painted different metallicity gradients of varying steepness onto the simulation. And we find that an initial metallicity gradient between -0.1 and -0.2 dex per kpc, which is very consistent with metallicity gradients that we observe in local group dwarf galaxies. Okay, so what do we learn from this? How does this help us in the question of what did Sag look like before it interacted with the Milky Way? Unfortunately, it doesn't directly give us the mass because metallicity gradient strength is not shown to correlate with stellar mass. That would be so convenient, alas. But one thing that it does that I want to throw out there into the world that I think is a really interesting direction forward is this question of whether or not Sagittarius had a disk. So this is a long-standing debate in the field of people modeling Sag. Did Sag have a disk? Was it rotating? And you get models that produce you can get models in both scenarios that produce different elements of the observations. And this has been recently revived in a really nice paper from Aurea, showing that a spiral disky structure in Sagittarius could be responsible for this feature known as the bifurcation in Sagittarius stream. But what I want to highlight is that if you have a disk at different inclinations with a metallicity gradient, you will get different metallicity gradients in your final stream. So I think this is one exciting study that I hope someone does, or I will do soon, to investigate this further. So I will leave my conclusions up and take questions. Thank you.
Questions for Emily? Okay, so Emily, like a few years ago, I was involved with this study with Ben Johnston where we had, gotten spectroscopic metallicities for one of the Sag stars, and we had ventured that maybe the dwarf galaxy itself might have like a stellar halo, like its own stellar halo, like these very metal-poor stars and these very outer wraps. So I'm curious if you see any, I mean, that was like hundreds of stars, and you now have so many more. So I'm curious if you see any.
So we do have many more, but we don't have as many as you all had in that study. And what Guilherme has in his study is RVs for a lot of these. We have the VP spectra, but not RVs. So we have RVs for about 7,000 stars, and all of them are following a very narrow track. So that specific question we're not getting at because it's the radial velocity dispersion. That's the real argument for if there was a stellar halo potentially, right? I found Guilherme's also argument that the enhanced velocity dispersion is lining up with the fact that you have previous graphs overlapping at low metallicity, also very compelling. So I think that's a great question that we need more RVs to investigate further, but that's not something we could get at with our particular data set. Yeah.
Great talk. I'm curious, is there any difference in like the IMF or anything like that when Sagittarius stars are just like a Milky Way?
That's a great question, and I really don't know. I mean, we're just looking at red giants. I should have said that. We're just looking at red giant branch stars here, so we weren't really getting at the IMF, but that is a really interesting question that I really don't know. And if anyone knows, please come tell me. Thanks.
Well, let's thank Emily for taking us in such a great way.
Great. Hi, everyone. Thank you for hosting me virtually. It's really good to be here and to talk about my research. I'm sorry I couldn't be here in person. So I'm a postdoc at Caltech right now, soon to be a Hubble Fellow at Stanford. And today I'm going to tell you about some of my work with cosmic rays. And just so that we're all on the same page about what I mean when I say cosmic rays are relativistic charged particles. And as you can see from this plot on the bottom left of the energy flux of cosmic rays as a function of their energy, cosmic ray can mean a lot of different things. They can be a lot of different species and a lot of different energies. So for the purposes of this talk, when I say cosmic ray, I mean primarily GeV protons, which make up like the vast majority of the cosmic ray energy density in the galaxy. And so what cosmic rays actually are these charged particles that move around magnetic field lines and then get scattered by fluctuations in those magnetic field lines, which is something I'll revisit throughout the talk. But if we want to study the effect of cosmic rays on the galaxy, we cannot simultaneously resolve cosmic rays as particles and their interactions with magnetic fields on AU scales simultaneously with parsec or kiloparsec scales that are relevant for galaxy formation. But luckily for us, on those larger scales, cosmic rays behave like a fluid. And as galaxy theorists, we know how to simulate fluids. So this is really good news for us. And this cosmic ray fluid affects galaxy evolution on all scales, starting from protoplanetary disks and star formation and giant molecular clouds, where cosmic rays can ionize and chemically enrich regions that are inaccessible to photons, to setting ISM structure and driving all sorts of instabilities, to launching galactic outflows that can extend megaparsecs out from the galaxy and continue accelerating gas in a way that thermally driven outflows don't. And in particular, for the last few years, I've been very interested in how cosmic rays can shape the circumgalactic medium around galaxies. And perhaps the most interesting result from my recent work and the work of other people who have worked on cosmic rays and the CGM has been that cosmic ray pressure just might be the dominant pressure source in the inner CGM around low redshift L-star galaxies. Now, there are a lot of qualifiers around that, but all these simulations that simulate Milky Way mass galaxies with cosmic ray feedback, by around redshift 0, and actually a little bit before that, they start seeing this cosmic ray pressure supported inner region. And there's a lot of weird implications for that for the state of the thermal gas. So for example, this is a simulation movie from idealized simulations of cold gas forming through thermal instability in a patch of CGM-like gas. And so these different panels show the density slices. And you can see on the left, without any cosmic rays, cold gas forms. It behaves like we expect cold gas to behave. It forms cold, dense clouds relative to the background hot medium. But as you increase cosmic ray pressure to the right, that cosmic ray pressure gets concentrated in the cold gas clouds, giving them extra pressure support so that cold gas can now form these very large, low density clouds that are buoyant in the atmosphere. And so they're not sinking. And this has all sorts of implications for the evolution of the circumgalactic medium and how it relates to gas accretion onto the galaxy and star formation and lots of kind of nonlinear effects. But the problem is that we can't actually discern, either definitively theoretically or observationally, the difference between these galaxies that are primarily supported by cosmic ray pressure in their inner CGM and galaxies where cosmic ray pressure is irrelevant in the CGM. And this is because it's extremely difficult to directly observe cosmic rays in the CGM, but also our theory could use a little bit of work. So I love using this cartoon plot to highlight the challenges facing cosmic rays in the galaxy. So the y-axis shows the kind of effective cosmic ray transport rate as a function of distance from the galaxy center. And this really highlights that all of our observations really only constrain the cosmic ray transport rate in the local ISM. And it's not at all clear how or if we can extrapolate those quantities from the local ISM out into other regions of the ISM of other galaxies, or the circumgalactic medium. And there really are models that can reproduce all of the observations in the local ISM, but then diverge from each other by orders of magnitude in their prediction for the cosmic ray transport rate out into the circumgalactic medium, which then has extreme variation in their prediction for how cosmic rays affect the structure of galactic halos. Now, I've been working on constraining this cosmic ray transport rate in the circumgalactic medium in two ways. One has been by directly trying to constrain this transport rate out in the circumgalactic medium. So this plot is from a recent work where essentially it's a slightly fancier version of this toy plot on the right, on the left, showing the average cosmic ray transport rate as a function of distance from the galaxy center. And in this paper, we made a toy model that can approximate the lower limit of the cosmic ray transport rate from 3 observables of galactic halos. And when we applied that model to the COS halo sample, we found a result. We found that just from this COS halo sample, we could see a clear trend in increasing cosmic ray transport rate out into the circumgalactic medium. And this gray band shows the expected, the average cosmic ray transport rate in the ISM of the Milky Way. And so if we expect other galaxies to have similar transport rates in their ISM, this clearly rules out models that do not predict an increase in the cosmic ray transport rate out in their CGM, which is a really good start. But as you can see, there's still a whole half of parameter space that is wildly unconstrained. And so another way of going about constraining cosmic ray transport is by trying to understand the underlying scattering physics on these AU scales that then leads to the bulk transport rate on galactic scales. Now, the good news is that we know the average cosmic ray scattering rate from observations really quite well. And so just to back up a little bit, this scattering rate is as cosmic rays move around magnetic field lines, there are small scale perturbations in the magnetic field lines on the order of a cosmic ray gyro radius, so that as this cosmic ray moves around the magnetic field, its pitch angle gets perturbed. And over enough perturbations and over enough time and distance, this leads to a bulk kind of flow of a cosmic ray fluid on galactic scales. And so we know this average scattering rate. We know that it is a power law as a function of the cosmic ray energy density. And we know how to take the scattering rate, plug it into our fluid equations. And when we simulate, or when we run simulations with this observationally derived scattering rate, we can reproduce all of the observations or all the existing observations. And this plot on the right is just an example of one such observation being reproduced, where the scattered points are observations and the lines are simulated data. But this is just to highlight that the observations are actually pretty robust for the average scattering rate. But the problem is that we don't actually have a working theory for what causes these magnetic fluctuations that then lead to the observationally derived scattering rate. And we do have theories, it's just that we recently found out they don't work. So the basic idea is these low energy cosmic rays, so in the MeV to TeV range, are accelerated by galactic supernovae. They then travel around tangled magnetic field lines before reaching the observer at or near the Earth. And traditional theories for cosmic ray scattering assume that throughout this entire cosmic ray path, there are these very small scale fluctuations in the magnetic field that are continuous and volume filling. But the problem is that by starting out with the assumption that these magnetic fluctuations are throughout the volume filling ISM, that means that in order to reproduce this observationally derived dependence of the scattering rate on the cosmic ray energy, you have to have a very specific power law spectrum of the magnetic fluctuations that we just can't quite predict like from theories. However, there's another way of interpreting the observations in an intermittent or patchy model of cosmic ray scattering, which is something that I've been working on very recently in collaboration with Phil Hopkins at Caltech. And so in this idea, you still start with cosmic rays being accelerated in galactic supernovae, traveling along tangled magnetic field lines. But the key difference is that rather than being scattered continuously, cosmic rays would free stream at the speed of light and only be scattered in these intermittent scattering patches every mean free path, which would be about 10 parsecs for a GeV cosmic ray. And by having this cosmic ray scattering only happen in these patches, you can kind of avoid the problem of requiring a very specific power law spectrum for the magnetic field fluctuations by instead invoking a size distribution of these scattering patches. And so in this recent work, we spent a lot of time kind of thinking through what would these scattering patches have to look like, and kind of what physical properties would they need to have, what number density would they need to have as a function of the size of these patches. And so in this plot, an ideal scattering patch would need to intersect these blue and green circles on the top right of this plot that show, so an ideal candidate would intersect kind of the required observational number density versus size for the MeV, GeV, and TeV cosmic rays. And on the bottom left in the dotted outlines, we plotted macroscopic ISM structures. So stellar magnetospheres, H2 regions, supernova remnants. And we find that these macroscopic structures are all immediately ruled out as candidate scattering structures. However, there are, sorry, I see some chats. Gotcha. 1 minute remaining. I will wrap it up really quickly. However, there are several other scattering structures that, or candidate scattering structures that aren't immediately ruled out, including intermittence and turbulence, tiny scale atomic structures or extreme scattering events, weak shocks or features in the magnetic field like mirrors or plasmoids that may still explain this cosmic ray scattering that we see today. And so I will be following up some of these scattering structures in idealized simulations to make predictions for how we can discern between patchy scattering and continuous scattering models so that we can constrain cosmic ray transport on galactic scales, and then that will unlock kind of predictive power in simulations for how cosmic rays affect galaxy evolution on all scales. So thank you for your time. I'm happy to take your questions.
Thanks so much for the nice talk. Time for questions. So I had a question about when you're trying to match the patterns in the CDM with the sources of cosmic scattering.
Can you stand in front of that owl?
Oh,
I
okay.
should be able to hear you better. So it's fine. It doesn't matter where for the owl.
Okay.
Somewhere here.
Okay. Put the mic. Okay. So how do you observationally detect these patches in the CGM?
Sorry, could you clarify which patches you mean?
Yeah. So the patches in the CGM that you correlating with the cosmic ray scattering.
I see. So the patches that I was referring to would actually, well, I guess they could be anywhere. We're going to start with the ISM because that's where we have the observational constraints for the cosmic ray kind of scattering data. Sorry, yeah, the average scattering rate. Observationally detecting them would be difficult. So one thing we can do is, like, if cosmic rays are scattered by these discrete structures, you would see like a slight overdensity in cosmic ray pressure and perhaps a change in the slope of the cosmic ray energy spectrum in those patches. So we could observe that either in gamma ray emission or in synchrotron. It's, you know, on the, using a back of the envelope kind of some predictions that we made in this work, it's unlikely that existing instruments can observe those differences. You know, you need higher resolution, but we're definitely going to do kind of more detailed follow-up work on specific, you know, mechanisms to see if there is something that we can predict observationally that we can observe now.
Great, thanks a lot. And one quick question while Maria is coming up and saying. Okay, so let's thank Iryna again.